Hello, welcome back. This video covers logarithmic functions, which is section 9.3. And this is one of my favorite things in the whole world. Anyways, we're going to be talking about converting between logarithmic and exponential forms. They are inverses of each other. The logarithmic function is defined as if x and b are positive real numbers such that b does not equal 1, that b does not equal 1, then y equals the log of x base b is called the logarithmic function with base b, where y equals the log of x base b is equivalent to b raised to the y power equals x. And depending on what we're trying to do, it is to our advantage to write it as an exponent or to write it as a log. So just a few things about this definition. Notice that x and b are positive real numbers. So that is, the base has to be positive, and also right here in the log needs to be positive as well. And so sometimes when we solve logs, we end up with what we call extraneous solutions because they end up being domain restrictions. And we'll get into that a little later. To start out, one of our first objectives is to write each equation in exponential form. So we're going to go ahead and do this. I like to tell my students it kind of like makes a little circle. You always start with the little number first, which is your base. You go across and you raise it to the power, and it equals the number there. So the equivalent exponential form of the log 16 base 4 equals 2 is 4 squared equals 16. Notice the base. When we write the log, the base is always the smaller number. On the other side of the equal sign is my exponent, and then it is equal to this part. Okay, let's try another one. So I start with 5, I go across to -1, and then back to 0.2. So 5 to the -1 power is equal to 0.2. And notice we're just rewriting it, we're not solving it or simplifying or anything like that. Okay, so you might want to pause the video and try 3 and 4. All right, so for number 3, I start with 8, which of course is my base. I go across the equal sign to my exponent, which is 0, and it is equal to 1. Okay, number 4. 23 to the 0 power is equal to 1. Okay, so that's one of our objectives, is to be able to take the logarithmic function and write it in exponential form. Now we're going to talk about what I would call the vice versa. That is, we're going to start with the exponent, we're going to write it in log form. All right, so for number 5, 2 to the 4th power equals 16. I would write this as the log, and I like to draw my L as a cursive L, just so that it doesn't look like a 1. So the log of 16 base 2 equals 4. That is read as the log of 16 base 2 equals 4. And if you want to pause the video and try the next two, go ahead. All right, number 6 would be, oh my gosh, okay, the log of 3 base 27 equals 1/3. So once again, the number being raised to the power is what we call the base. And of course, the exponent is in the exponential part. All right, number 7 would be the log of 16 base 1/4 is equal to -2. And what's cool about this is if you wanted to check it, you could just rewrite it in the opposite form, right? So I could just come over here, and if I wrote this as an exponent, it would be 2 to the 4th power equals 16. And that's how I could check it. Okay, well, there's a few things that you should know. First is that the log is probably in your calculator somewhere, so you might want to just look for that button. We'll be using it a little bit later on. But one thing we're going to talk about is how to evaluate log expressions. And so when it says evaluate the log of 144 base 12, it is helpful to rewrite it as an exponent. All right, so this would be 12 raised to some power is equal to 144. Okay, that's basically what this is saying, is that 12 raised to some power is equal to 144. And we have to figure out what that power is, right? So you could maybe use a calculator. You might know that x is equal to 2, or that, the question mark is equal to 2, but I just end up with 2. So this whole thing gets replaced with a 2. And if you have a scientific calculator, you might just look. Sometimes if you hit the log twice, it'll allow you to type it in just as it is, but we will talk about some calculator issues a little later on. Okay, so what does this say here? This says 64 raised to some power is equal to 8. Well, I know that the power has to be less than 1 because I'm going from a bigger number to a smaller number. And I know that the square root of 64 is 8. So I could write this as 1/2. Boom. And that is 64 to the 1/2 power equals 8. Right, so I could check this for sure with my calculator. So 64 to the 1/2 power is equal to 8. So 1/2 is my answer. All right, for number 10, 3 raised to what power is equal to 1/27? Well, the fact that this is a fraction would mean that my exponent has to be negative. So I have to think 3 raised to what power is equal to 27? Okay, I know that would be 3, but because it's 1/27, I know it's going to be a negative 3 since it's a fraction. All right, there are some other important definitions with logs. One is called the common log function. The common log function says that y equals the log of x base 10 is written as y equals the log of x. That is, if there's an invisible base, it is assumed that the base is 10. The reason why is because base 10 occurs in the real world all the time. It models noise levels, it models pH balances, it models earthquakes. And so a long time ago, they decided that if there is no base here, it is assumed to be 10, right? It's kind of like how the square root of 25 is equal to 5, and we know it's the square root, but there's an invisible 2 on our index. It's very similar. This has an invisible 10. And in your calculator, you most definitely probably have log base 10. And so you might look to see if you have the word log. Well, another very important definition with logs is called the natural log function. Y equals the log of x base e. We know that e is approximately 2.71828, blah, 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 goes on forever. It occurs in nature all the time. It's so special. It gets its own log, and it's y equals ln of x. But really, I want you to know that we call it the natural log. So ln is basically log natural, or natural log, and you also probably have the ln button in your calculator as well. And a lot of times it's actually next to the letter E, which is cool. All right, so let's talk a little bit more about different things we can do with logs. And this is really the introduction to logs. That's why this section is kind of long. Okay, we're going to evaluate each expression. Now at this point, you may want to use a calculator just to see what kind of calculator you have. It's very difficult as a teacher to help you because everybody has different calculators. So just do your best to look for the log key. So if I type in the log of 100 into my calculator, I get the answer 2. And the reason why is because the base is 10. It's invisible, right? But we know that this is the log of 100, base 10. So this says 10 raised to what power equals 100? Well, 10 squared equals 100. And then for this one, it's very similar. So you might try to type it into your calculator kind of to see what your calculator can do. But if you do this by hand, it is a very small decimal, which means my question mark must be negative. And then I would just figure out, okay, how negative is it? 1, 2, 3, 4. So that would be 10 to the negative fourth is equal to 0.001. You can definitely check that with a calculator, so you end up with negative 4. And I just want to point out that on number 11, 10 squared does equal 100, right? Okay, so let's talk about 13 and 14. When I have the natural log of e to the negative third power, this is basically saying e raised to what power equals e to the negative 3 power. Well, that's pretty easy. That would just be negative 3. And then on number 14, this says e raised to what power equals e to the 10th power. Well, that's pretty easy. That would just be 10. And you can try that one in your calculator as well if you'd like. All right, well, it's really important that we have a calculator to help us with logs because we actually have to use a calculator for certain questions. And a long time ago in antique math books, you can go to the very back of the book and there are these extensive log tables that they used to have to use. So we are going to use our calculator to find the approximate value. We're going to round our answer to 4 decimal places. We'll check our answer by using the exponential form. So this is where you need to take a look at your calculator. You may be in base 10, you might not be in base 10. It just depends on what type of calculator you have. So if you type in the log of 200, you should get approximately 2.3010. And if you're having trouble, so if you just type in the log of 200 and you don't get that, you might have the option of doing the log of 200 base 10. Some calculators actually want you to put that base in, and it is 10 since there is an invisible base, okay? And then I'm going to show you how to check this in blue. Basically, 10 raised to 2.3010 is approximately 200. Okay, that's how I would check that. Okay, now let's try number 16. So the log of 0.074, when I type it into my calculator, I get approximately negative 1.1308. And to check, which I'll do in blue again, 10 raised to negative 1.1308 should be approximately, it's approximate because we rounded, 0.0740. Check. Okay, now we have the natural log. You should have that natural log button somewhere in your calculator. Please type in the natural log of 200. You should get approximately 5.2983. To check it, which I'll do in blue again, I would do e raised to the 5.2983, and I should get approximately 200. It's like 199.9965, right? Because we did round, so we got to keep that in mind. All right, so for number 18, I type in the natural log of 1.005. I get approximately 0.0050. And to check this, which I'll do in blue again, I'll do e raised to the 0.005, which is approximately 1.005. Okay, so that's how we check it. Everybody has a different calculator. I'm not going to try to figure out every single calculator that exists, but you can always ask me questions or send me an email or remind if you need help with your calculator. Okay. Now we're going to move on to some very fun basic properties of logs. Basic properties of logs. All right, so there's quite a few. It says that if you have the log of 1 base b, it equals 0 because b to the 0 power equals 1. Yes, awesome. Anything to the 0 power equals 1, except for 0, that's undefined, but you don't have to worry about that because that would be a domain restriction in the first place, right? By definition, b has to be a positive. Okay, so let's try, b has to be greater than 0. Okay, so here's another one. The log of b base b equals 1 because b raised to the first power equals b. Okay, the log of b to the x power base b is equal to x because b to the x equals b to the x. And last, b raised to the log of x base b equals x because the log of x base b equals the log of x base b. So these are very basic properties. I would say that they're so basic, they almost naturally happen when you're solving the problem, especially if you just write all of these as exponents or logs, depending on what you start with, you're going to notice that that would happen anyways. All right, so we're going to go through some of these together. All right, so we're going to simplify each expression. My advice is to always write it as an exponent first if it's in log form. So for number 19, I can think of this as 19 raised to some power, which is why I put a question mark, equals 19. Well, that's easy. That would just be the first power. And so that is using the property right here, right? Okay. Number 20 says the log of 10. Well, really what that is 10, because the base is 10, raised to what power equals 10? 1. 10 to the first power equals 10. Number 21, I see the natural log of e. E raised to what power equals e? Because remember, the natural log of e has a base of e. It's of course invisible, and it's assumed. So that would also be 1. Okay, now on 22 and 23, they're going to be very similar. I have the log of 1 base 273, which could be thought of as 273 raised to some power equals 1. And this will say 1/8 raised to what power equals 1? Well, anything raised to the 0 power equals 1, except for 0, that's undefined. But you don't have to worry about that because that's not going to be in our domain anyways. All right, 24 says 30 raised to some power is equal to this, 30 to the 10th power. Okay, well that would just be 10. Okay, and then right here, e raised to some power equals e to the negative 12 power. That's just negative 12. So the hope is that you can start to identify some of these properties and you can do them a little bit quicker, right? All right. These next two, we're going to be applying the property here, which says if you have b raised to the log of x base b, it's going to equal x. And so the base here is 10 and the base here is invisible 10, which is just going to be 14. 27 follows. The base is 8 here. The base is 8 here. So we end up with just 5. All right, that is an introduction to logs, but we're not finished. We do need to talk about what logs look like graphically. So let's take a look at what that looks like for our graphs. So we have the graph of y equals log of x base 3. What we can do to help us is we can rewrite into exponential form and select values of y first. So the exponential form of this expression, would be 3 to the y is equal to x. Okay, and then what I'm going to do is I'm going to be plugging in values for y. And the reason why I want to do that is because I can evaluate it much simpler by doing that. If I plug in values for y, I'm going to be able to easily find x. All right, and we're just learning what that logarithmic curve looks like. Okay, so when I plug in 0, 3 to the 0 is equal to 1. When I plug in 1, 3 to the first power is equal to 3. 3 squared is equal to 9. 3 cubed is equal to 27. 3 to the negative 1 power is equal to 1/3. 3 to the negative 2 power is equal to 1/9. 3 to the negative 3 power is equal to 1/27. Okay, so logarithmic functions and exponential functions are inverses of each other. So you're going to see that this graph is the inverse of 3 to the x power, and they would actually reflect that line y equals x if we graph them on the same plane. Okay, so let's go ahead and start graphing. Now remember, our ordered pairs are just going to be 1, 0, 3, 1, 9, 2, and so on, right? These are my ordered pairs for the graph. So I'm going to start with 1, 0, which is kind of difficult to do because of the increments that they gave us. And then 3, 1, it's a little easier to do. 9, 2, 27, 3, And if you look over here, 1/3 negative 1 would be like right there. And then 1/9 negative 2. Okay, so you can see it's going to be kind of difficult to continue to graph. But what happens is we're going to get infinitely, we're going to get infinitely closer and closer, but we're not actually going to cross. Okay, so I apologize that I'm not a perfect person, with my graphing, but really that's what the curve would look like. It'd be more smooth. So I'm going to try to, maybe I can do this, get this to look a little better. I think it's actually this ordered pair that's not helping me out. There we go. Okay, I'm gonna make this look a little nicer. I'm gonna try. Oh, geez, I don't know if that's any better, but basically this is what the curve of it looks like for the logarithmic curve. Okay, so let's try 29. Well, what we can do is we can actually apply transformations of logs to help us. So this is not really new. You've seen it in the past. You saw it with when we had transformations, and you also saw it with exponential functions as well. So all the transformations that we've learned still occur here. So my parent function, you could think of the parent function as y equals the log of x base 2. And what would happen is we would shift that left 1, since this is a plus 1, and up 2, right? So let's go ahead and plug in some values for x to see what happens. All right, so I'm going to start with 0. When I plug in 0 here, I get something that looks like this, right? Because 0 plus 1 is 1. So 2 raised to what power is equal to 1? Well, that would be 0. And 0 plus 2 is equal to 2. So at 0, 2, I would have an ordered pair. And then when I plug in 1, so now I'm going to plug in 1, I will get the log of 1 plus 1, which is 2, base 2 plus 2. This is saying 2 raised to what power equals 2. That's just 1, and 1 plus 2 is 3. So 1 comma 3. And then when I plug in 2, well, that's a decimal. Okay, that's going to be approximately 3.6. And so I could probably use a calculator to get that decimal. And I will try to graph it the best I can. So 2 and 3.6 would be like, or maybe right there. And then when I plug in 3, I get the log base 2 of 1 plus 3 plus 2. This becomes the log of 4 base 2 plus 2. But this says 2 raised to what power equals 4? That would be 2. 2 squared equals 4, and 2 plus 2 equals 4. So 3, 4 would be another ordered pair. Now when I try to plug in -1, I get 0, and we can't have the log of 0. So it's actually undefined at that spot. So I don't have to worry about my -1 value. And then if I try to plug in maybe like -1/2, I end up with 1. So it looks like this. So there's basically an asymptote at -1. And the reason why is because when we plug in -1 here, we end up with a 0. And if you try to find the log of 0, your calculator might explode, or it'll just tell you no. It's not part of the domain. All right. So in general, here are some informations about the graphs, because we don't expect you to graph this by hand all the time. That would be just crazy. So here are some examples that may help you. So as long as b is greater than 1, then y equals b to the x, you can see here, is in blue, and the log of x base b is in red. there is that graphic feature I was talking about since they're inverses of each other. And then we have a little summary that might help you right here. So we've got the domain and range, the horizontal and vertical asymptotes for each one respectively, and the ordered pairs that they pass through, which is really cool. So remember, because they're inverses of each other, the domain becomes the range becomes the domain, the horizontal asymptotes become the vertical asymptote. If it passes through 0, 1, it's going to pass through 1, 0. Okay, so hopefully that helps you when you're thinking about those graphs. All right, woo, we're almost done with this long section. The last thing we're going to be talking about is the absolute magnitude. This is just an application. There are many applications to logs. The absolute magnitude m of a star is the apparent magnitude m a star would have if it were placed 10 parsecs from the Earth. The lower the value of the magnitude, the brighter the star. Our sun has an apparent magnitude of negative 26.74, the brightest star in our night sky. The brightest star in our night sky is Sirius, the dog star. That is also in Harry Potter, by the way. I'm a big Harry Potter fan. Anyways, with an apparent magnitude of negative 1.44. The sun appears so bright because it is very close, astronomically speaking. The formula m equals little m minus 5 log d over 10 relates a star's absolute magnitude, apparent magnitude, and its distance from Earth in parsecs. If Sirius is 2.637 parsecs from Earth and the sun is 4.887 times 10 to the negative 6 parsecs from Earth, what is the absolute magnitude of each star? Okay, whew. So they're asking us two questions. So I'm going to start with Sirius. And we've got the magnitude, the apparent magnitude is negative 1.44, which in our formula is right there. And then they have to also give us the distance, which is 2.637. And that's going to go right here in our formula. Okay, so we're just taking the information they gave us, and all I'm going to do is plug it in to my formula. So this seems like a very difficult problem, but it's really not that bad. So m is equal to negative 1.44 minus 5 log of 2.637 over 10. Now you'll notice that in this formula, the base is 10 because it's not written, right? So you, depending on what kind of calculator you have, because you're going to use a calculator for this problem for sure, you need to be aware that the base is 10. For some of you, it will naturally be 10 in your calculator. For others, you'll actually have to put in a little 10 right there. Okay, I did it in red for you. If you do this correctly, and you would type it in all at once exactly as it looks, you should get approximately 1.45. So that would be the absolute magnitude, which is big M, okay? That's for Sirius. Now, how about the sun? Well, they had to give us information. So they gave us the apparent magnitude, which is little m, is negative 26.74. The distance is 4.887 times 10 to the negative 6 power. All right, so you can see the distance is pretty far, right? So now what we're going to do is we're going to plug in what we know into our formula. So we have negative 26.74 minus 5 log of the distance, which is, for the sun, 4.887 times 10 to the negative 6 power divided by 10. All right, so now this whole thing would go into my calculator. Depending on what type of calculator I have, I might have a little, I might need to actually type in 10, or it might already be in base 10. When I type all of that in, if if I do it correctly, I should get approximately 4.81 for my absolute magnitude, which is much less bright than Sirius if you compare the 4.81 to the 1.45. All right, that's it for this section. I hope this helps, and I hope you have a great day.